Error checking. So often we get to a scenario where we have to send or receive data, and there's a need to check if the error, if there's any errors that you've maybe received in that string of data. It might be that you're transmitting from one microcontroller to another microcontroller some information. We might be sending from a computer to a microcontroller information, or vice versa. So often it is why you at the transmission station, you want to make sure that message goes through correctly, because if there's some other error that might happen, your receiving station could execute the wrong instruction, which could be devastating. So that's the reason why there's often some error checking methods that are used. So I'm just going to go through a few of them that are quite often used and that might be useful for projects. So the first one we're going to be looking at is parity checking. So you've got two types of parity checking. You've got odd parity checking and even parity checking. And these are often used with serial communication as well. You'll see if you set up your serial communication parameters and settings, it will always have a thing of like 8 parity, or we have 8 bits, maybe it might have even parity checking or odd parity checking. And whatever parity checking system you got in place, you just need to make sure that you've got it both at the transmitter and at the receiving point the same. So now it basically works as if we had to use even parity as an example over here. We're going to ignore this bit over here, this 8th bit, if we had to read it from the left to right. Okay, so we ignore that bit over there. And usually you will be transmitting 7 bits to represent a character. Okay, so in this case we've got 101101. Okay, so with even parity, you want to make sure that you've got even number of ones that are being transmitted always. So what you'll do is you'll count how many ones you've got. Now keep in mind, you're ignoring this one over here. That one doesn't exist at the moment. Okay, so we've got 101101. That's the number that we've got at 7 bits. So if we count how many ones there are, and that's with where the cursor is now over the one that we aren't able to see, you'll see there's 1, 2, 3, 4, 5 ones. Now that's an odd number of ones. So for us to make this an even number of ones, we have to add a 1. So we add 1 at the end of the number. So when you get to the receiving station, what the receiving station will do is say, okay, well, have I received over here even number of ones? If it has, it will say, okay, then that character's been correctly received. If not, it will either ignore the instruction or request that the instruction gets sent again, or that specific character gets sent again. Okay, so once it's done that and it identifies whether this is a valid parity in terms of being an even parity, or this even number of ones over there, it will then go and reject this one over here and then read the rest of the numbers. So it says 101101, and that obviously won't be there. Okay, again, if you look at the odd parity, with odd parity, it looks at how many at the odd number of ones must be valid. So again, it ignores this bit over here, 8th bit, and it looks at the first 7 bits. And how many ones are there? There's 1, 2, 3, 4 ones. Okay, so now to make it an odd number, to make it 5 ones, it's going to then have to add a 1. So then it adds a 1 over there for the 8th bit. Again, gets to receiving end. The receiver goes and checks it and says, okay, well, I know I'm using odd parity. That is the agreement we've got between the transmitting station and the receiving station. Let's look at how many ones I've got. 1, 2, 3, 4, 5. Okay, that means that number, or that set of binary numbers are correct. It goes and rejects the last number then, and then says, okay, well, what is the interpretation of these 7 bits in a specific number or character? Okay, so that's parity checking. It's often used at sort of the microcontroller hardware level of communication, but it can be useful for different type of tasks. Again, used a lot for the serial communication. So often you do see that there are these settings that you need to set to validate if it's even parity or odd parity, and that is essentially what it means when it does this. Right, cyclic redundancy checking, or CRC. Okay, so this is achieved by doing modular arithmetic. Okay, so modular is determined as in the following example. So if you've got 35 mod 9, that's equal to 8. Okay, so how was that answer achieved? Well, it's 35, as you would have basically done in grade 1 math. It would be 35 divided by 9. How many times does 9 go into 35? It goes in 3 times. And what's the remainder then once you've got 3 9s going into 35? Well, the remainder is 8. And that remainder value is what is the answer. So 35 mod 9 is equal to 8. When programming in C, instead of using mod, you would actually use a percentage sign to represent the mod function or operator. Okay, so these can be quite useful. Where it could be useful is, for example, if you look at your ASCII numbers, they are ranging from, or at least all your normal characters like your alphabetical characters and your digits, they would range in be from 0 to 127. Now, there's a few more characters in between over there, but that would be sort of the range of characters that are printable. So essentially, you could go and essentially write a program that would send out a string of characters, and it will. So if you want to, for example, send a string of cyclic redundancy checking CRC in brackets, you could actually go and look at what the ASCII value is for each specific character, add them up all together, and then once you've done that, you're going to then mod by 127 and look at what the remainder is, and that will be another character you'll send at the end. So now when the receiving station receives a string of characters, it will do the same. It's going to go and add the ASCII value of all the characters together, and once it's done that, it will mod it with 127, and it will check if the remainder value or the answer is the same as the one as the last character being received. This could also be a way of possibly doing some form of not encrypting a message, but maybe verifying if a message is correct. You might have a transmitting and receiving station, and you could find a modular of a certain number. It could be any number. I mean, you could still use the ASCII numbers as your numbers that you are going to be adding up together. But you could say, you know what, just to make sure that we've got some or other, if I can call it security to some sense between the transmitting and receiving stations, so that there isn't any message received from a third party that you're not aware of. You could then go and implement this CRC system, have it, let's say, modular 20, and that 20 might be the agreed value that you've got between your transmitting system and your receiving system. See if that final character matches up with that character that it's supposed to do. If you add all the character values together and modular that by 20, and then if it is, then you know, okay, there's a good chance that this packet of data or this string of characters is accurately received. Okay, then another form of error checking that can be useful to use is in barcodes. So barcodes is something that is often used to validate if a certain parcel has been received. It's being used to track items. So as you could have a parcel that's been posted around the world, and every time it goes to a different location station, they scan it, and then they're able to keep record of where the parcel has been going and traveling, and you can track it in online to see where it's going. Okay, so this barcode that I've got over here is from a 363 music CD, and it's got the numbers 804-147-143329. You'll see that 9 is a very small 9 over there. Okay, so these lines in the barcode, it's not very clearly shown over there, but those lines are representing some or other binary format of this number. Okay, and you've got your center double lines as indicated over there. Okay, so this barcode essentially sort of represents two different things. It's the first set of numbers, which could be up to those numbers over there, could represent a certain product, or it could be, well, not necessarily in terms of a product, but it could represent a specific company that produces these products. And then the last set of numbers can represent a specific product that company is manufacturing. So it all depends on how the barcode is made. Sometimes you've got some companies that might have a few more numbers. If you look at your typical retail store or shopping place that you go and do your normal shopping at, they might have longer numbers because they've got quite a large variety of products that they're selling, and from different companies. Okay, so these barcodes, I mean, like you do to get different barcodes, you get your QR codes, you get different new types of barcodes as such that are coming out. We're not going to go into all the different types of ones, but I want to go sort of through the way that it has got some checking digit in it and how it's obtained, and verified if that barcode's been read properly or not. So keep in mind, you go into the shops and you buy a product, and the part's taken through that laser scan, and then it goes teet, and then it's like, oh, okay, well, it's read the price correctly. Has it read the price correctly? I mean, how do you know it didn't read maybe some other number of another product and it scans through? And that's essentially how we're able to verify it. What happens if somebody should go and try and erase one of those lines on a barcode? Or what should happen if somebody should color in a line on the barcode? So you're able to actually verify all this. Okay, so to do this is quite a simplistic way of calculating it. And these are essentially the steps that you've got to follow. Okay, so if you look at this number over here, we're going to ignore this number 9. So the barcode is actually 804-147-14332. So the 9 does not exist when we read it. Well, at least we might read it and we might see it as coming in as a 9, but we will ignore it for now. Okay, so we add all the odd numbers and multiply the answer by 3. So we take, when I say odd numbers, it's the odd position numbers. Okay, so the first position is the odd one, the third position is the odd one, the fifth position number is the odd number. Those are odd position numbers. Okay, so over here we've got 8 plus 4 plus 4 plus 1 plus 3 plus 2. Okay, so if you add 8 plus 4 plus 4 plus 1 plus 3 plus 2, that's equal to 22. Multiply that number by 3 and we get 66. Okay, so now we leave that answer 66 aside, and then we go and we look at all the even position numbers, and we add them together. Okay, so that would be like 0 would be the number position 2. 1 would be number position 4. Okay, so we'll carry on like this. So that's 0 plus 1 plus 7, okay, plus 4 plus 3. Again, we ignore the number 9 over there. Okay, so when you add 0 plus 1 plus 7 plus 4 plus 3, we get 15. Now we take that 15 and we add the 66 that we added in, or that we just calculated. We add that 66 to 15 and we get the answer of 81. Okay. Now this check number, which in this example is number 9, essentially what we do is we say, okay, well, this 81, how many digits is required to get a number that's multiple of 10? Okay, so the next multiple of 10 number is 90. Okay, so we need 9 digits to be added to, or the number 9 to be added to 81 to get 90. Okay, so that's where you get that 81 plus 9 is equal to 90. So that 9 is then used as your final digit, which is your essentially your error checking digit for binary, or at least for a barcode. Okay, so this is a very brief overview of 3 different error checking methods that can be performed, and that you might even come across, or that you might not even be aware of, that is being used, like this parity checking. It's happening in the background and you're not even aware that the system is using it. But it can be useful when you come across that. The cyclic redundancy checking can be useful just to check if a string of characters have been received correctly. Do a modular operation on it, see what the remainder is, and use that as your error checking for the string. And again, the string, you're essentially going to be looking at the ASCII table, and each character obviously has an ASCII number, and you can add those ASCII values together. And then we had to look at barcodes, which looks at your number, splits it, well, ignores the last digit initially after it's read, looks at all the first number, or all the odd number positions, and adds them together, multiply it by 3 and get an answer, and then add to that all the even position numbers, obviously except for the number, the error checking number, number 9. Look at what the answer is, then look at how many digits is required to be added to that to get to the next multiple of 10, and then use that as your error checking. If that value that you've calculated correlates with the number that's on the barcode, you know you've read the barcode probably correctly.